Hey, BC Calculus. This is day one of the course. So in the beginning here, we're going to be jumping into limits, and we're also going to try to give you a little bit of sense of what this course is about. So it's a little intro to the ideas of the course, and then also some technical stuff. So let's get to it and move me out of the way. So you should have the note sheet that's available to you, and it shows you what we're working on here. So this first activity I normally do in class, but we're going to do this digitally instead. And so I'm just going to run through it instead. I'm not going to try to like pause it a lot. I'm just going to kind of go through it. And so you should be following along and pausing to re-listen to anything if you have any questions, and of course contacting me if there's anything that's not clear. So here's what it is. So sneak peek of calculus. Here's a graph of f of x. Okay, there's f of x. Mark points on the graph where x equals 1 and x equals 5. Okay, I can do that. Piece o cake. Woohoo! What is the value of f of 1? Remember, f of 1 is asking what the y value is when you ask this question. And so when the x is 1, the y is 2. Right? Your answer to number 2, because this. Your answer to number 2 represents a length. Draw a segment to show where that length is, and label it. So this is always a little bit tricky because there's a little bit of read my mind going on here. But here's the segment I'm going to think of is that distance right there is f of 1, right? It's that length is f of 1, okay? And for each of the following values, find each of the following values and draw a segment. Okay, so here's the segment for f of 5, right? And f of 5 is 1, 2, 3, 6. F of 5 is 6, right? And this is 2. Cool, I can do that. And then I'm supposed to, that's this one, check, that's equal to 6. And f of 5 minus f of 1, and I'm supposed to draw a segment that relates to that. Well, if this is f of 1 and this is f of 5 over here, then the difference between the two of them, since they're both vertically oriented, is just like that part cut off, and it's this part right here, right? And why don't I label that a little bit better just to make it a little easier to see. And I say, okay, this distance right here is f of 5 minus f of 1. Ooh, doesn't let me write out there. Okay, minus f of 1. That kind of makes sense. All right, so that distance right there is f of 5 minus f of 1. And so it's this squiggly over here. And that's equal to 4, not because 5 minus 1 is 4, but because 6 minus 2 is 4. Right. So now what does that expression represent? And so it's this distance right here divided by 5 minus 1, which is that distance right there. And so it says draw on the graph to clarify and find the value. Well, it's 4 over 4, which is 1. But what does that stand for? If I do this divided by this, please notice the scale isn't the same, so it's not even here. And that is just the slope of this line, right? That slope of that line. It's just changing y over changing x. So I'm looking at this expression going, whoa, that expression looks pretty complicated. But actually, it's just slope is all that thing is doing, okay? All right, we drew on the graph. Okay, good. All right, so now we're going to go to the second one. Whoa, change of pace. So I actually looked up the data for the first month of the COVID epidemic, and I looked at the number of new cases each day in Washington State, and then fit an exponential model to it, which was pretty good for the first month. A model doesn't always work forever, but it worked for that long. And it says, so there's the function, and it's the number of days. So, and all you're supposed to do, or x is the number of days. And all you're supposed to do is find what these expressions are, and I've got my handy dandy calculator, and then explain what each one means. Just to save a little time so you don't watch me pushing buttons, I'm going to find all these values by plugging 10 in, or 30, or 10.5, or whatever, into the function, and then working all these. So I'm going to pause it, I'm going to work those things out, and then we'll talk about them. You could try that too on your calculator. Okay, I just accidentally hit the start button, but fortunately I had just finished and written the last number. So whoa, okay, let's get ready. So So I just plugged the numbers in. One thing to note here that's important to do is whenever you're rounding for the purpose of this year, always round to 3 decimal places. That is the standard for the AP test. So if you're used to significant figures or something like that, let it go. For the AP test, if you round, you have to round to at least 3 decimal places. And so just always round to 3 and then move on with your life. Okay. So the first time I did, so these are all the numbers, but now we need to know, well, what do each one of these things mean? So, and I hope you know that that's an exponential function. You should have seen that last year. And so, it looks something like this, right? That's a very, very crude, actually, that's such a crude graph that I feel kind of embarrassed about it. So let's make it, because it's really slow and then it really cranks up in the end. That's just the way the data went that I looked up from earlier this year. And so if you kind of think about, like I said, okay, so what is this thing saying? So when you go to 10 here, 10, then the model is giving us an answer of 21.052. And what this says is that the model, 10 days after February 27th, then the model predicts that there would be 21-ish new cases that day. I mean, obviously, it's not going to be perfect. This data wasn't exactly on here. It was kind of scattered around there. It was actually pretty exponential, though. The R squared was very good, and so a decent approximation of the number of new cases 10 days after February 27th was that. Next one, that would be the difference between the number of new cases. Again, it's always predicted by the model on day 30. I'll just call it day 30 for now. It's always with reference to February 27th. The difference between day 30 and day 10. Hold on one second. Sorry about that. We just had a little noise here. Woo, COVID. Okay. So the difference between day 30 and day 10, according to the model, is that there were 786 new cases each day. That's how much the difference was. That's again predicted by the model, so it's not the exact number. Now the next one gets interesting. So now it's okay. So there's 786 is the difference over 20 days, and so that's the rate of change that you should have studied in some kind of in your algebra classes talking about rate of change. Is that then there's that on average it was going up about 39 new cases each day for every day for those 20 days. It doesn't mean it was going up exactly that every single time. It just means that on average, that the number of new cases, if you watch the new case meter and you watch how the days were going, that the number of new cases was going up 39-ish cases per day. Yeah? And now we get to this next one, which is kind of interesting. Again, I just did it on the calculator, didn't do any math out of the calculator, do all the work, made sure the answer was plausible, made sure I had my parentheses in the right place. So now we're saying, okay, between 10.5 and 10, and I know it's a little silly because this data obviously was just once a day, but what we can think about is, so if you go from 10 to 10.5, then the average rate of change between those is that it was going up about 4 cases per day during that little window of time, like again predicted by the model. So we can go, wow, that's like when I find the 39 number, if you think about this graph, so imagine it's like here and here and here's 30, that when you find the average rate of change there, that in the beginning it was going up a lot slower and in the end it was going up a lot quicker. So that's just the average, and it's not telling you what's happening at 10 or at 30 or specifically anywhere in between. I guess there's one day where it would be about the same amount of tiltiness, but otherwise it's just giving you an average. But now when we go 10 to 10.5, then we're looking on a little narrow window of time, at a very small window of time, and so that's a much better prediction of what's happening at 10 days. So that's giving me a pretty good idea of at 10 days, it's going up about 4 cases per day according to this model. Yeah. So the last part of this first window into calculus is that we had 2 expressions there, but I didn't use the same words for both. So this is what we used in the first one. This was in the second one. Pause the video, take a second and think about what did those things mean in each problem, because even though the expressions are about the same, I talked about them differently. Don't review the video. If you're not sure, you could write down what you remember, but don't feel like you have to get this right. But just say, well, what did I talk about when I talked about each one of those expressions? I'm going to pause it so you can think about it a second. So what you should have thought about there, if you had the stuff right, is in the first example, we talked about this being the slope, right? We talked about that being the slope. So we talked about it geometrically. But in the second one, we talked about this as the average rate of change. So that's kind of interesting because they were used in two different senses. And even though the expressions are basically the same, that one situation we're talking about the slope between 2 points, and in the other one we're saying what's the average rate of this thing that we're measuring, the average rate that it changes over that time. Because it's changing, scroll. It's changing at different amounts as time goes on. It's really cranking up at the end of it, but in the beginning it wasn't changing very much at all. So the purpose of this first stage is to kind of give you like something to go to think about, and think about the connection between slope and average rate of change. That's often covered even in Algebra 1 class. Sometimes they talk about slope being the average rate of change. What got a little bit different, was a little bit extra, was this discussion right there, which was, wow, if I could kind of narrow my window and look over a smaller range of time, then I'm kind of like, I'm finding out more, not about the average, but about what's going on at that moment. By having a smaller window, I'm seeing more about what's happening specifically at that time rather than over a long period of time. And that's kind of like, that's all you need to do for today is just go, I know it's clearly with the gray beard, it's a lot more profound, but you have to do what you can. So that's the intro to the topics. Next time, we're going to start looking at limits, which are how we're going to address these slightly weird questions. So hope that made sense. And we should have with the video discussion of if you have questions or comments or things, how you take care of that. So please look where the video is posted for information about that. Thank you.